This is the second part to inference. So this is the, or variance inference, which is the two-sample one. We did the single sample last week, which uses the chi distribution. So again, there's many distributions. We've generally done Z, T, chi, and then this week we're doing F. So we've covered 4 different types of distributions. Those aren't the only 4. There are many others. There's gamma. There's a whole bunch of them. You can probably find a web page like Wikipedia or something like that as a whole list of them, and they, depending on what the situation is what you use essentially. Um, so um, F distribution, which F is the Fisher, the same Fisher. There's the 1/20th rule there with the 5%, same guy. So if you have 2 independent chi-squared random variables, right? So hence the 2 sample. They have 2 different degrees of freedom, obviously, or they could have the same, I guess. It's a ratio. Okay, and basically when you look at the ratio, if they're the same, it would equal 1. If they're not the same, it would not equal 1, right? Essentially, correct? And the thing is to keep in mind when you do these, you always want to put the bigger one on the top and the smaller one on the bottom. There's some intricate reason as to why that is. And so a lot of what we're going to do this week is the video. So I have an F distribution video there and a confidence interval video there I want you to watch. And then for the hypothesis test, I gave you 3 videos. This one is doing the problem I'm going to do today as a confidence interval. And this is a nice overview one, basically. Okay, so these are going to use the problem I'm doing. And this one is just a nice overview one I want you to watch, basically. Okay. So the F distribution is going to change. It's another, so the chi and the F are both the 2 asymmetric or non-symmetric distributions, where the Z and the T are the symmetric distributions. So the chi varies because of a single degree of freedom. This function is going to vary by 2 degrees of freedoms, right? The 2 different ones that are involved, basically. Obviously, so therefore it's another skewed distribution, basically, just like chi. The area, of course, no matter whether it's Z or T or chi or F, the area of the curve is always still 1. Okay. All right. So if you have 2 samples, right? The uppercase n just means the overall population. The lowercase n is the number that's in the sample, right? So for confidence interval you're doing, right? You have an upper and you have a lower. So let's say you're doing like a 95%, right? 95%, right? That means your alpha would be 5%, right? Right? Because 1 minus alpha, 1 minus 5% would give you 0.95, correct? For doing the Fisher rule, right? Which means alpha divided by 2, right, would be 0.025, correct? Okay, so this would be 0.025 F value. This is a right tail, by the way. This is the right tail. Makes sense on the right side. So this would be 1 minus that, which would be 0.975 F value, basically. Okay? If you're going to use the right tail test, or if you just do the regular old F instead of that. But we'll go over that, basically. Okay? So the confidence interval is either written like this, or it's written like this. Either one is equivalent mathematically. So the F 1 over the F value and the ratio of these sample standard deviations, and then 1 over the F ratio and the standard deviation ratios, basically. Okay, so let's say I want to do a 95% confidence interval for these 2 sets of data, population A, population B. Let's do that and interpret it, essentially. So, all right, so I put it in a spreadsheet, which I'm going to give you. So I did my sample standard deviation, so standard deviation dot sample, correct, of the first column. And I did the sample standard deviation of the second column. And if you square them, you obviously get the variance, because the square root of the variance is the standard deviation, right? So the first set has 16 values, the second set has 22 values, right? Although it goes to 23. There is a header on here, which is why it's 22. So the degrees of freedom is 15 and 21. Yeah, I know that the formula has n twice, like n1 and n2, but I did m, so I could differentiate it. Some books use m and n, some use n1, n2. It doesn't really matter, right? Okay, so so basically again same um, picture. Since we're doing since we're doing 95% confidence, alpha is 5%, right? Which means this end over here, this is f of 0.025, right? That's our alpha divided by 2 value, right? Because obviously it's 2.5% on either side. Okay, so I need to do a f inverse right tail to get the f value on that x-axis, right? Of 0.025, and you want to do the um, numerator and then the denominator there basically, right? And if you notice that this one right here is bigger, right? Let's see if I can draw that. This one is bigger and this one is smaller. Therefore, this is the numerator, right? And this is the denominator in the ratio of them basically. Okay? All right. So there's a couple ways to go about, oops, crap. A couple ways to go about it. You can just do 1 minus that to get the 0.975, right? Keep it as a right tail. Or you can just simply get rid of the right tail and put that in, right? And you'll get the other side. So either way, when I graph this, it's not really, it's a curvy, it's asymmetrical one. Right? You're going to get an f value here and an f value here, right? This f value is this one, right? That's the f value there, and that is the f value there, correct? Okay. All right, so again, there's two ways to go about it. So there's this formula here, which goes to these ones, and then this formula here goes to these ones. So either way, less than or equal to, 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 right? Variance over variance. I can't make a very good variance symbol there, right? So the true population falls between 0.83 and 5.81, right? So essentially, if I do this one here, it's larger deviation divided by, sorry, larger variance divided by smaller variance divided by alpha, right? Too. So that's right. This one to here. So I just kept doing division, right? And then this one goes to here. So essentially, I'm doing the bigger divided by smaller variance divided by the f alpha divided by 2, because that's the 1 minus 1, right? So if I look at the formula there, it goes to there. And then this one, slight differentiation, it is a ratio times, again, the standard deviations, bigger divided by smaller, and the same thing here, right? So it's just a matter of a copy dot flip difference. So you'll see different slight variations, but they're all mathematically equivalent across different textbooks and web pages. You'll get the same answers though. One big difference you'll see is a lot of them are still doing paper tables, which is kind of ridiculous. So you have to do some extra finagling for those, but don't worry about that. Everybody either uses software, spreadsheets, or handheld calculators that can do the calculations now. So it's kind of silly, right? Okay, so let's interpret the answer, right? Because if you look at what this is saying, what is it saying in context? So we're 95% sure the true population variance is going to fall within this range. That's what we think, correct? Okay. So again, we are 95% sure the true population variance is going to fall within this range, which means 5% of the time we're probably going to be wrong, right? What conclusion can be made about the hypothesis test, and are the two populations different, and how do you know? Well, it's a ratio, right? If you look at the formula, it's a ratio, correct? So if the populations are the same, then this ratio would equal 1, correct? But you notice that the 1 is in the confidence interval, right? Which means the hypothesis test, you're probably not going to reject the null hypothesis, right? Because this is going to be the null hypothesis, essentially, that there's an equal ratio. So you're not going to reject it. Therefore, they're probably not different, right? Because whatever, so the sample we got, right, this is a common sample. It's probably in here, basically. Okay? That's what we're concluding. So that is what it tells us about the so that's what the confidence interval tells us, essentially, in this case, that these two population variances probably not equal, probably not different, right? never confident on those. Okay, so then the last part of this, I want you to watch these videos using the same problem for hypothesis testing. And keep in mind that all of these distributions we've done, there are formulas for these particular curves. So the z curve for the t, for the chi, and for the f, right? So when you go to graduate school, that's when you do the formal statistics, which is when you actually do the area under the curve without using a computer. Because we're using Excel to cheat, basically. So if you do calculus, right, you do what's called an integral, right, which from A to B, right, from A to B, right, will figure out the area under the curve. So essentially, you're not doing the calculus part, you're just doing like the intro to statistics part by getting the answer from this using the spreadsheet without actually doing the calculus. So the difference between your college level and your graduate college level is then at that point you know the calculus and you're doing the actual calculus functions and proving them, so you don't have to actually use a spreadsheet to get the actual incremental values. You actually understand where they come from. At this point, you just know what I'm looking for is you know the distributions, when to use them, and then how to get the answers, but not necessarily how you get the calculus part of it.